All right, we will continue. It's our second video about similarity and diagonalization. So, theorem 4.23, very important theorem. So let A be an m by n matrix. Then A is diagonalizable if and only if A has n linearly independent eigenvectors. So if and only if, again, here we are using, it has two implication, that is I, F, F, or we mean this. So that means that if A is diagonalizable, then A must have n linearly independent eigenvectors. Or if A has n linearly independent eigenvectors, then A must be diagonalizable. So more precisely, there exists an invertible matrix P and a diagonal matrix D such that P inverse times A times P equals D. That's from the definition of a diagonalizable matrix. If and only if the columns of P are n linearly independent eigenvectors of A, and the diagonal entries of D are the eigenvalues of A corresponding to the eigenvectors and P in the same order. Okay, so to prove actually this, we assume that A is diagonalizable. So now we are going to show that then A has n linearly independent eigenvectors. Okay, so suppose first that A is similar to the diagonal matrix D. And also we know that from the definition, A is similar to the diagonal matrix D if there exists an invertible matrix P, right, where P inverse times A is equal to P inverse times A times P is equal to D. Or if you just multiply both sides by P on the left, and we get this equation, and we know that these two equations are equivalent. AP equals PD. Okay, now we just use this equation that AP equals P times C. That means that A is similar to the diagonal matrix D. So now suppose that also the columns of P are this P1, P2, dot, Pn. So we are just partitioning matrix P in this way. So here the first column is vector P1, the second column is vector P2, dot, and the nth column is vector Pn. And we know that these vectors are from, or is it n-dimensional space. And here I change from 1 to n. And let the diagonal entries of D be this, since actually D is diagonal matrix, and we are just assuming that the diagonals are here. Don't get confused. I'm not claiming that these are the eigenvalues. Okay, I'm just actually the entries in the main diagonal, just using these variables. So here we have lambda 1, dot. Here we have 0, 0, lambda 2, dot. Here we have 0, dot, 0, dot, 0, and here we have lambda n. That is our diagonal matrix D. Okay, so now here it's given that it's given that A times P is equal to P times D, right? So we are going to show that actually these vectors, what is it? That A has n linearly independent eigenvectors. All right, so now, if you just substitute into the equation A times P, right here we know that A times P is equal to P times D. And here we have matrix A. P is partitioned in this way. Here P1, P2, dot, Pm. On the right here we have matrix P, and here we have matrix D, right? And actually I can bring this A inside, right? We know that this is just column and A times P1, A times P2. If you just bring the matrix P inside this matrix, then we will have this matrix on the left, A times P1, and the second column, A times P2, and the nth column, A times Pn. What are these? We know that actually these are the columns of the product A times P, right? On the right, if you multiply that thing by this matrix, for example, the first column by this one, we will have lambda 1 times P1. And lambda, this should be lambda 2 times P2, and this is lambda n times Pn. Okay, So we will continue. After all, we'll just substitute those things into this equation. That's it. Okay, here we have lambda 1 times p1, lambda 2 times p2, and lambda n times pn, right? On the left, we have n by n matrix. This one is n by n matrix. On the right, we have n by n matrix, right? And what are the corresponding columns? That is the first column, and also that is the first column on the right. And that is the nth column of the matrix on the left, and this one also the nth column on the right. And we know that two matrices are equal to each other if their corresponding components are equal and they have the same sizes, right? And also their corresponding entries must be equal to each other. That means that the first column on the left must be equal to the first column on the right. And the second column on the left should be equal to the second column of the matrix on the right, and dot, dot, dot. And nth column on the left should be equal to the nth column on the right, right? Also, we know that actually in the definition, when we are giving the definition of this similarity, right? And we know that actually we have a condition here. P must be invertible. P must be invertible means that what we need, we know that P is invertible means that the rank of P is equal to n. It means that it has n linearly independent columns. Actually, the columns of P are this P1 and P2 and Pn. And also, if you just look at these things, what we have here, A times P1 equals lambda 1 times P1. That means that P1 is an eigenvector of matrix A, right? With respect to this lambda 1. And also, P2 is another eigenvector of A, actually corresponding to, with respect to this lambda 2, right? So that means that it's P1, P2, P, and these are the eigenvectors of A, and corresponding eigenvalues are lambda 1, lambda 2, lambda n. And we know that from here, the columns of P, that's P1, P2, P, and these are linearly independent vectors, which means that actually these eigenvectors are linearly independent. Conversely, if A has n linearly independent eigenvectors, so how about this way? Now we assume that A has n linearly independent eigenvectors. Let's say those vectors are P1 and P2 dot dot, and here we have Pn, right? With corresponding eigenvalues. Corresponding eigenvalues lambda 1, lambda 2 dot dot, lambda n. Then we can just write these equations then, since these are eigenvectors, right? These are eigenvectors and corresponding eigenvalues are this, then it must satisfy this equation. A times P1 should be equal to lambda 1 times P1. And A times P2 should be equal to lambda 2 times P2. Dot dot. A times Pn should be equal to lambda n times Pn, right? Actually, this implies the above equation. That equation is, what is it? A times P equals P times D. And also, which is equivalent to our original equation. And consequently, if we take P to be the n by n matrix with columns P1, P2, and Pn, that equation, our first equation becomes AP times PD. Since the columns of P are linearly independent, the fundamental theorem of invertible matrices implies that P is invertible, so that P inverse times A times P, that is equal to D. That is, A is diagonalizable. You're just moving backward here. Good. Now we get something new. Let's just use this theorem to solve here. We have two equations. Okay. How does it look? Okay, not bad. So if possible, find a matrix P that diagonalizes this matrix, right? And also we know that for this matrix to be diagonalizable, its eigenvectors must be linearly independent. So now let's find its eigenvalues. So the solution, okay, first, what are the eigenvalues? Here we have determinants of A minus lambda I, which is, here we have minus lambda 1, 0, 0 minus lambda 1, 2 minus 5, 4, minus lambda, right? Which is equal to, if you actually compute this determinant, here we have, okay, okay. So here we have minus lambda along the first column, right? Here, if you just delete the first column and the first row, here we have minus lambda, 1, minus 5, 4, minus lambda. And the second one is 0, it is plus, minus, plus. So here we have plus 2 times, delete the third row and the first column. Here we have 1, 0, negative lambda, and here we have 1, which is equal to minus lambda. The first one is minus minus, so here we have lambda squared minus minus 4 lambda, and the minus 5 is plus 5, plus 2 times 1 times 1 is 1, and here we have 0, so here we have just 2, which is equal to, okay, all right, so here we have minus lambda, and it will have cubic equation. So let's just keep this minus out here. Okay, just keep writing green. So minus, what do we have here? Lambda cubed minus 4 lambda squared plus 5 lambda, and here we have minus 2 because minus 1 is here. It's a cubic equation now. Here we have equals, this thing is equal to 0. So we have to solve this equation. And we know that actually we solve cubic equation by factorization. The actual roots must be one of the factors of this two. Sorry. The first step, the second one. So what are the factors of 1? 2 is plus minus 1 or plus minus 2. So let's say now that thing is P of lambda. So let's just check here. For example, if lambda equals 1, what do we have here? Here we have 1 minus 4 plus 5 minus 2. That's equal to minus 3 minus 5, that's equal to 0. Okay, that means that lambda 1 is equal to 1. We got the first eigenvalue. How about negative 1? If it's negative 1, here we have P of negative 1, that's equal to minus 1, minus 4, minus 5, minus 2. And as you see here, it's not equal to 0. So we have nothing to do here. How about if P equals 2? If the lambda equals 2, here we have 8 minus 4 times 4, that is 16, plus 5 times 2, that is 10, minus 2. From here is 18. Okay, that's also equal to 0. That means that here we have another eigenvalue. Let's say that is lambda 2 is equal to, what is it? 2. And if it is minus 2, minus 8, so it is minus 10, minus 18. Here we have minus, okay, 4 minus 16. Okay, it will not be equal to 0. So now we know that two factors of this cubic polynomial is the thing, lambda minus 1 and the lambda minus 2, which is equal to lambda squared minus 3 lambda plus 2. And dividing this polynomial by this expression, we can find the third one. Okay, just if you just divide this, you will see that actually also the third one will be 1. Okay, so here I can just write here, let's say this one is lambda 3 and the lambda 1 and the equals lambda 2, that's equal to 1. Then we can just write those things. So here we have that polynomial is equal to like this. Here we have minus lambda minus 1 squared times lambda minus 2. Is that right? Here we have 2 and here we have 1. So which means that lambda 1 equals lambda 2 equals 1, and lambda 3 is equal to 2. Okay, so now first, actually this is step 3. So now we will find the eigenvectors corresponding to these eigenvalues. So if you just consider the first one, you just change the marker here. Okay, so we use reds. Okay, then augmented matrix will be, here we have 1 1, sorry, or 0 1 0. So here we have minus 1, right? Minus 1 1 0. So here we have 1 0, and the last column is 0 0 0 0 1. So here we have 0 minus 1 0 0 0 1. Okay, 0 0 1, and the last column is 2 minus 5 4. Here we have 2 minus 5 4. 4 minus 1 is 3. Right? And the last column is 0. I'm not writing this. So what do we got here? Okay. So here we have, if you just add the second row to the first row, here we have minus 1, here we have 0, here we have 1, or here we have 0, 1, minus 1, multiply the second row by negative 1, and here we have 2 minus 5, 3, right? Or here, multiply the first row by 2 and add to the third row. Here we have minus 1, 0, 1, 0, 1, minus 1. So minus 2 plus 2 is 0. So here we have nothing. And the minus 2 plus 3, that's equal to 1. Right? And also, if you just multiply the first row by negative 1, here we have 1, 0, 1. Here 0, 1, minus 1. Multiply by 5, the second row by 5, and add to the third row. Here we have 0, here we have 0. 5 minus 5 plus 1, that's equal to 4. Right? Okay. Again, I can just multiply, what is it? Here we can just write here this as, what is this? Okay. So that is 1, and add to here, and also add here. Here we will have 0, 0, and 0. Okay, so I think we can make a mistake here. Let me recalculate the thing. All right, just this way. Okay, here, let's multiply the first row by negative 1. Here we have 1, minus 1, 0. Also here by negative 1, 0, 1, minus 1. And here we have 2, minus 5, 3. Okay. So here we have 1 as a pivot. Also this one is pivot. Let's add the second row to the first row. Here I have 1, 0, minus 1. Here we have 0, 1, minus 1. Right? Here we have 2, negative 5, and 3. All right. Here, if you just multiply the first row by negative 2 and add to the third row, we have 1, 0, minus 1, 0, 1, minus 1, minus 2 plus 2, it is 0. Here we have nothing. Minus 2, that is 2 plus 3, that's equal to 5. Now, as you see here, the third row is just a multiple of the second row. So here we have 1, 0, minus 1, 0, 1, minus 1, 0, 0, 0. Okay. So from here, let me just write eigenvectors for I1 equals I2 equals 1. The eigenvector is what is it? Equals from here, x1 minus x3 is equal to 0. x2 minus x3 is equal to 0. That means that x1 equals x3, x2 equals x3, all are equal to each other. So actually, one basis vector is this, 1, 1, 1. Okay. Now, how about this? Lambda 3 equals 2. If you find the eigenvalue corresponding to this, here our augmented matrix, here we have 0, so here we have minus 2, 1, 0, 0. Here we have minus 2, 1, 2, negative 5. Here we have 4, 4 minus 2, that's equal to 2, right? So, all right. Okay, the first one, let's just add to the third row. Here we have minus 2, 1, 0, 0, minus 2, 1, minus 2 plus 2, it is 0, 1 plus minus 5, minus 4, 0 plus 2, it is 2. Now, if you just multiply the second row by negative 2 and add it to the third row, here we will have also multiply by, the first row by minus 1 over 2. Here we have 1, minus 1 over 2, 0, 0. Here we have 1, minus 1 over 2. Here we have 0, 0, 0. Or one more. Let me just write here. Multiply the second row by half and add here. So here we have 1, 0, multiply by half. So it is minus 1 over 4. 0, 1, minus 1 over 2, 0, 0, 0. So what we have here? Here we have x1 minus 1 over 4, x3, that's equal to 0. And x2 minus 1 over 2, x3, that's equal to 0. So if I just take this x3 as, let's say, 4t, right? And what will be one eigenvector corresponding to this eigenvalue? We just write here, that vector will be, here we have x1, x2, x3. That is, x1 is here 14, that is t. When t equals 1, let's say when it equals 1, here we have 1. And x2, that is when it is 4, that's equal to 2. And x3, it will be 4. Right? So that is our second eigenvector corresponding to this eigenvalue, and that is the first one. And we are talking about a 3 by 3 matrix, right? All other eigenvectors, actually, either it's just a multiple of the first eigenvector, or it is the scalar multiple of the second eigenvector. So we have only two linearly independent eigenvectors. That means that this matrix is not diagonalizable. Okay. Okay. So another example here. So here it's just actually is the upper triangular matrix. So actually it's, the eigenvalues are displayed here transparently. From here we can just find that here the first observation is lambda 1 equals lambda 2 is equal to 1, right? Because 1 minus lambda, 1 minus lambda, so lambda should be equal to 1. And lambda 3 should be equal to 4, right? Because all the entries in the main diagonal in upper triangular matrix or lower triangular matrix, actually they are just the eigenvalues of the matrix. Okay, so now corresponding to the first one, let's work on the first one here. Okay. Let's find the eigenvectors corresponding to these eigenvalues. So if we form our augmented matrix again, 1 minus lambda. So here we have 0, 1, 0, 0, 1 minus lambda. So here we have 0, 1, 0, 0, 4 minus 1, that is 3. And if you just reduce this to reduced row echelon form, here, let's see, 1. If you just multiply the second row by negative 3 and add to the third row, what do we have here? Here we have 1, 0, 1, 0, 0, 0, 1, and 0, 0, 0. Right? Which means that here we have x is anything. Here we have x1. What is x1? It doesn't appear in the equation. It's any real number. x2, right, is equal to 0. x3 is equal to 0. So one eigenvector corresponding to this eigenvalue, then it is this vector. Here we have 1, 0, 0, when p is equal to 1. And how about the second one? When it is 4, right? When eigenvalue is equal to 4, we find the corresponding eigenvector. Here we have 1 minus 4, 1 minus 4. So here we have minus 3, 1, 0, 0, 1 minus 4, minus 3, 1. And here we have 0, 0, 4 minus 3, that's equal to 1. So if you reduce this to reduced rational form, so we will have here something like this. Okay, here multiply the first row by minus 1 over 3. Here we have 1 minus 1 over 3. Here we have 0. The same thing. Here we have 1 minus 1 over 3. And here we have 0, 0, 1. Right. Okay. So from here, actually, minus 3, 1, 0, 0 minus 3, 1. Okay, 0, 0. So, okay, this is 4. Okay, all right. So 1 minus 4, 1 minus, okay, this should be 0. Sorry, this should be 0. This should be 0. Okay. So from here, and again, if you just multiply the second row by 1 over 3 and add to the first row, here we have 1, here we have 0, 1 over 3, right? That is 1 over 3. Okay, you just multiply 1 over 3. So here we have minus 1 over 9. So here we have 1 minus 1 over 3, 0, 0, 0, 0. Which means that x1 minus 1 over 9 x3, that's equal to 0. x2 minus 1 over 3 x3 is equal to 0, right? For example, if you just take this x3 as 9, for example, that x1 will be 1, x2 will be 3, and x3 will be 9. Okay. So this we are talking about 3 by 3 matrix, and here we have two linearly independent vectors. So it is not 3. If actually this matrix A is diagonalizable, then it must have 3 linearly independent eigenvectors, right? And the theorem says that if it is not, then this matrix is not diagonalizable. Okay. So now we'll see the last equation, and I think we are hoping that this will be diagonalizable. I'm not sure. All right. So first we need to find actually the eigenvalues. The first step, okay. So determinant of A minus lambda I, which is equal to determinant 1 minus lambda, 1, 4, 0, minus 4, minus lambda, here we have 0, minus 5, minus 1, and here we have minus 8, minus lambda. Okay, now how to calculate this? Here we have 1 minus lambda, and delete the first row and the first column. Here we have minus 4 minus lambda, 0, minus 1, minus 8, minus lambda. And here it is 0, and the third component is minus 5. So we should delete the third row and the first column. Here we have 1, and here we have 4, minus 4, minus lambda, and here we have 0. Okay, which is our characteristic polynomial. And if you just evaluate this, I will just skip the computation part. We will get this polynomial, that P of lambda will be equal to lambda plus 4 squared times lambda plus 3, which implies that actually the solutions of this equation is lambda 1 equals lambda 2 equals negative 4, and the lambda 3 is equal to minus 3. Okay, now we'll just find the corresponding eigenvalues, the eigenvectors. The first one, let's say the second step here, lambda 1 equals lambda 2 equals negative 4. So then the augmented matrix here will be 1 minus minus 4, minus 4 minus 5, right? So 1 minus minus 4. Here we have 5, 5, and here we have 1 and 4. Here we have 0, minus 4 minus 5, right? That's equal to, is minus 4. No, actually 1 minus minus 5, minus 4 minus 4. That's equal to minus minus 4. That's equal to 0. And here we have 0. Here we have minus 5, minus 1, minus 8, minus minus 4, which is minus 4. And as you see here, if you just add the first row to the third row, we will have that thing. 5, 1, 4, 0, 0, 0, 0, 0, 0. Or here we have that 1, 1 over 5, 4 over 5, 0, 0, 0, 0, 0, 0. Which means that here we have x1 plus 1 over 5 x2 plus 4 over 5 x3, that's equal to 0. I just need only one eigenvector. So one eigenvector corresponding to this eigenvalue will be then if, okay, I need more space, I think. Let's continue here. So here we have x1 plus 1 over 5 x2 plus 4 over 5 x3, that's equal to 0. We have two independent variables here, free variables here. Let's see from here, if x2 equals, let's say, what is it, 5s, and x3 is equal to 5t. Then we will have what we have here. Then x1 will be x here, x2, 5, 5 cancel each other. That is minus s and minus 4t, right? So this eigenvector, I mean, the basis will be actually here. The eigenvector will be just linear combination of these vectors, s times, here s is a common factor, here we have minus 1, x2 is 5, here we have no s, plus, and t, and here we have, what is it, t, in x1 it is minus 4, in x2 no t, in x3 we have 5. So these are two basis vectors that spans the eigenspace of this eigenvalue. Okay, we got two vectors. And how about if lambda is 3? If lambda is 3 equals negative 3, right? So our augmented matrix will be here. It is 1, 1, 1, 4. Okay, those things. So what we have here, it is 1 minus minus 3. Here we have 4. Here we have 1 and 4. The second row is 0. Here we have minus 4 minus minus 3. That is minus 1. Here we have 0. And the third line is minus 5 minus 1. And minus 8 minus minus 3. That is minus 5. Right? Okay. So here, if you just add that thing to the first row, I mean the first line and third line, what do we have here? The first, I can add the second row to the first row, and also first multiply the second row by negative 1. Okay, here we'll have 4, 0, 4, 0, 1, 0. I multiply the second row by negative 1, and also actually multiply by negative 1 to the first row. And also add it to the third row, what we have here, minus 5, 0, minus 5. Or that is what we have here. Here we have 1, 0, 1, 0, 1, 0. And if you just add, divide by 4 and multiply by 5 and add to the third line, here we have 0, 0, 0. So here we have x1 plus x3, that's equal to 0. The second line, x2 is equal to 0. So from here, what we have here, x1 equals, let's say, minus t, x2 equals 0, x3 is equal to t, where x3, just take x3 as a t. So one eigenvector corresponding to this eigenvalue will be then, what is it? If t equals 1, for example, here we have negative 1, 0, 1. Okay, so now we get three vectors. You can check that actually those vectors are linearly independent. So if you just write here, here we have minus 1, 0, minus 1, 5, 0, minus 4, 0, 5, and the third vector is minus 1, 0, 1. So I can just write here, then here that matrix P is columns must be these vectors. The first one is minus 1, let me just write like this. Okay, so it is diagonalizable because it has three linearly independent eigenvectors. The columns of P will be P1 and P2 and P3. What is P1? That's the first basis vector. That is minus 1, 5, 0. And P2, here we have minus 4, 0, 5. And P3, it is minus 1, 0, 1. Right? These are the eigenvalues. So this one is P1, vector P1, and this one is vector P2, and this one is vector P3. So now I can just write it like this then. Matrix A, here we have A times P equals P times D. What is matrix A? Our original matrix. Here we have original matrix that is 1, 1, 4. Here we have 1, 1, 4. And the second line is 0, minus 4, 0. 0, minus 4, 0. And third line is minus 5, minus 1, minus 8. Minus 5, minus 1, minus 8. Times matrix P, that is minus 1, minus 4, minus 1, 5, 0, 0, 0, 5, 1, which is equal to, again, matrix P here, minus 1, minus 4, minus 1, 5, 0, 0, 0, 5, 1. And here we have diagonal matrix. So here, this one is P1, P2, P3. It must be in the right order. So here we have lambda 1. What is lambda 1? Lambda 1 is minus 4. So here we have minus 4, 0, 0. Lambda 2, also minus 4. It is 0. 0, 0, lambda 3 is minus 3. Okay, so the given matrix is diagonalizable because it has three linearly independent vectors, and this is how we write the matrix P and matrix D. Thank you.